to each other by what is known as the gas laws. Now let's talk about basically the pressure. Let's start from pressure. Now the pressure of a gas is basically proportional to the height of that gas in a in something like a gas manometer. So that's what we talk about in the episode where we talk about heat measurement. We talk about the principle of operation of a gas manometer. So you can know that the pressure is proportional to the height. So if we use such a manometer, the pressure due to the height of water is equal to the pressure due to the height of another related height of mercury. The only difference is that in these two, the pressure depends on the density, and the height also depends on the density. So in this case, you can write the h, the product of the height and the density and the acceleration due to gravity in the left hand of the equation is equal to the product of the height, which is y, and the second density, which is the density of the mercury by the acceleration due to gravity. Now these terms on the left side and the right hand side of the equation, they have the dimensions of pressure. So now we can say rho 1 is the density of water, rho 2 is the density of mercury, and using rho 1 is equals to 1 gram per centimeter cube, and rho 2 is 13.6 gram per centimeter cube. We can write y equals hp1 over p2. That's h over 13.6. So that's 13.6 is the ratio of the density of water to the ratio of density of mercury. Now in this case, when we perform these evaluations, we can say h centimeter of water exerts the same pressure as y equals h over 13.6 centimeter of mercury. That means you can see that the height of water which can exert the same pressure as water is dependent on the density. So in this case, we have the gas pressure as given by P equals H plus H over 13.6. So this is the amount of pressure. Now this pressure is equal to 76 plus H over 13.6 centimeter of mercury. Now this pressure, you can see that there's a direct relationship between pressure and the height. So and this pressure and the height is also related to the centimeters of mercury. So in standard notation, 760 is 76 centimeters of mercury. It is the standard atmospheric pressure. Now this is an example of the setup where we make use of the difference in height of the columns of mercury in the two limbs of this manometer to measure the pressure. So in this case, you can see the height. So the difference in height, it amounts to the pressure or the pressure of the gas, or the pressure difference between the gas and the atmospheric pressure. Now let's talk about a barometer. A barometer is an instrument that is used for measuring atmospheric pressure. We can construct a simple barometer by taking a clean, dry, thick-walled glass tube about 1 meter long and filling it completely with mercury. Then you cover the top of the tube with a finger and invert it so that all the tiny air bubbles collect together. Then you turn the tube round again and finger. Fill the tube again completely with mercury to exclude all the air. Then you close the mouth of the tube with a finger and invert it into a dish of mercury. Now when you remove the finger and observe the level of the mercury, you will see that it falls into the tube to a height h as shown. So measure this height above the mercury level in the open dish. And since the air was completely excluded, that means this space is a vacuum, and it's called the Torricellian vacuum in honor of Torricelli, who first made a simple barometer using mercury. Now it is generally known that the height of mercury in the tube above the mercury level in the dish is found to be 76 centimeter or 760 millimeter. So this is the height of mercury that can be held by the atmospheric pressure. So the simple barometer is not an accurate instrument as it can contain air or water vapor instead of vacuum, and it is also bulky and not convenient. So because of this, there are several other types of barometers that are used to measure pressure. Now in practical use and realistically, we mostly use two type of barometers, and those are the 14 barometers and aneroid barometers. Now let's talk about the 14 barometer, and this is it in the diagram here. This 14 barometer, it is used for measuring atmospheric pressure in the laboratory, and it gives a more accurate reading than the simple barometer. It is basically a simple barometer enclosed in a metal case with a glass window through which the mercury level can be seen at the top and bottom of the metal case. So as you can see, this is how it looks. So instead of the dish in the simple barometer, we have a leather bag to contain the mercury, And before taking the barometer reading, a screw at the lower end of the bag is used to lower or raise the level of mercury in the bag until it touches the tip of an ivory pointer. So the height of the mercury level is then measured from the tip of this pointer to the level of mercury in the barometer tube. So that's how you measure the height, and this gives a more accurate measurement than the simple barometer. It is used practically. Now, folks, let's talk about one part of gas laws that's very important, and that is known as the Boyle's law. And Boyle's law expresses the relationship between the pressure and the volume of a fixed mass of gas, and is given that the pressure of a fixed mass of a gas is inversely proportional to its volume, provided that the temperature is kept constant. So in symbols, Boyle's law is written as P is proportional to 1 over V, or PV is a constant. So what this means is that if the volume increases, the pressure will decrease. If the volume increases, the pressure will decrease, and vice versa. So there's an inverse relationship. Now, here's an example that is related to the concept of Boyle's law. In this case, we are told that the pressure of a fixed mass of gas is 960 millimeter mercury. When the volume of the gas is 3 meter cube, find the pressure of gas when its volume is 4.5 meter cubes. Assume that the temperature is constant. So in this case, we are going to make use of Boyle's law, where PV is a constant at constant temperature. So therefore, you can say P1 V1 at a particular condition is equal to P1 P2 V2 at a second condition. So when we substitute in our values, we will make P2 the subject of the formula. That would be 960 times 3 divided by 4.5. So we have 640 millimeters of mercury as the pressure. That means when its volume is 4.5 meter cube, it will have a corresponding pressure of 640 millimeters of mercury. Apart from Boyle's law, there's another gas law which is known as Charles' law. And this Charles' law gives the relationship of the volume of the gas to its temperature at a constant pressure. So in this case, we have Charles' law states that the volume of a fixed mass of gas increases by 1 over 273 of its volume at 0 degrees Celsius per degree Celsius rise in temperature, provided its pressure remains constant. So Charles' law gives us a relationship between the volume of a gas and its temperature, provided that the pressure is constant. So that means that because this is a direct relationship, that means as the volume increases, the temperature will increase, and vice versa. So when the temperature decreases, the volume will decrease correspondingly. Now, because of the fact that the volume is directly proportional to the temperature in Charles' law, we can use this knowledge to draw a graph, and this graph is the statement of Charles' law, and can be derived from, and this statement can be derived from the graph of volume against temperature at a constant pressure. So in this case, the temperature is in Kelvin. So this is absolute temperature in the horizontal axis against volume in the vertical axis. When you sketch it for an ideal gas, you get a straight line. Then when it is traced backwards, it will cut the temperature axis at minus 273 degree Celsius, or 0 Kelvin. Now this is the temperature at this temperature. This is temperature at which there is zero volume. So this is where the volume cuts the temperature axis. So basically, this is quite let's call it's a little bit, it's a surreal phenomenon, because it's not possible for a gas to have zero volume. Instead, the gas becomes liquefied. But that's one of the things that differentiates ideal gases from real gases. But basically, we have what is known as the cubic expansivity, and which is defined as the increase in volume per unit volume per degree rise in temperature of the gas. So what this means is the change in volume with respect to the original volume with respect to time. So that is equals to 1 over 273. That's basically the cubic expansivity. Now, in general, the cubic expansivity of ideal gas is 1 over 273. That's the factor, because that is the increase in volume per unit volume per degree rise in temperature of most gases. So, and then we know that VO over 273 is a constant. So we can say that V is proportional to temperature. Now, here's an example that demonstrates Charles' law. In this case, we are told that the volume of a fixed mass of gas at a constant pressure at 200 centimeter cube at 0 degrees Celsius and 295 centimeter cube at 130 degrees Celsius. We are asked to look for the cubic expansivity of the gas. So we'll make use of the formula. The cubic expansivity of a gas is given as the change in volume divided by the original volume divided by the product of the original volume and time. So basically, and temperature rather. So basically, the change in the volume is 295 minus 200 divided by the product of the um original volume and time is 200 times 130. So we get an answer of 0.00365 per Kelvin. So this is the cubic expansivity of this gas. Now finally, there's a concept which we will talk about in this video, and this is the concept of the general gas law. Now we can deduce the general gas law from Boyle's law, Charles' law, and the pressure law. From Boyle's law, we have that PV is constant if T is constant. From Charles' law, we have that V over T is a constant if P is constant. And then from the Gay-Lussac's or pressure law, we have that P over T is constant. So the pressure law, which I did not state in this video, is a law that is a consequence of the Boyle's law and Charles' law, and it states that the pressure of a gas is directly proportional to its temperature at constant volume, provided that volume doesn't change. So that is it says that pressure is directly proportional to temperature. Now, any two of these three equations can be combined into one equation to form PV over T will give a constant. And this constant means that PV over T is a constant for a gas. So that means P1 V1 over T1 equals P2 V2 over T2. Now, this is for two different conditions. On the left hand side, we have the first conditions where the first condition as the subscript. Then on the right hand side, we have the second conditions as subscript of each of the properties of the system. Now these general equations can be used to connect the three properties of a gas, and it's very important in gas laws. Now in summary, today we've talked majorly about the gas laws, which include the pressure law, the volume Boyle's law, and the Charles law. Now thank you for watching this video to this extent, and today we are done for this episode. This is a question on the screen for you to try out. You can also show me your answers as a comment in the video, or you can send to the number at the end of this, at the description of this video. So I will see you next episode.